In this lesson, we're going to be talking about compound events. Compound, just like a sentence being a compound sentence, there's more than one. We're talking about compound events now. So with compound events, there's more than one event happening. What's the probability that this happens, and then this happens, and then this happens? You might have multiple events going on. Now, before we had simple sample spaces, such as flipping a coin. You're either going to get heads or tails. It's simple. Rolling a dice, 1 through 6. You're going to roll one of them. But now our sample spaces are a little bit more difficult. And I'm going to show you, first off, the longer way of doing this, but I want you to be able to create sample spaces. The first one says a standard coin is flipped. Okay, so let's start with that. So when you flip a coin, your first event, you're either going to get a heads or you're going to get a tails. Now, after that, you roll a dice. So what if you got a heads? Okay, there's 6 different possibilities of what happens now. 1, 2, 3, 4, 5, and 6. You might get a heads and a 1, a heads and a 2, a heads and a 3. And you could even list that if you wanted to. You could get heads 1, heads 2. And you could list all of these different events. Then, what if you got a tails? You could get the exact same thing. These 2 events are what's called independent. The first one does not impact the second one. If the first one, let's say that if you get a heads, you're more likely to get a 6, and that's not true. That would be called dependent events. So now let's go through and find this probability now that we have our sample space. And again, our sample space is heads 1, heads 2, heads 3, all the way through 6. Or you could get a tails and a 1, a tails and a 2, tails and a 3. So what we're looking for now, it says, what is the theoretical probability of getting a heads and then an even number? So the probability, we're going to take this path. We're going to get a heads and then an even, a heads and an even, a heads and an even. Now, a lot of people like to count that heads as a single event, and they'll do heads as 1, 2 as 1. That's not right. Your events, the way that this can happen, you could either get a heads and a 2, a heads and a 4, or a heads and a 6. That's the only 3 ways it could happen. Now, let's talk about the total ways. You can get heads 1, heads 2, all the way through 6, or tails 1, tails 2, all the way through 6. There's 12 different ways. Now, I'm going to go ahead and introduce you to what's called the counting principle. The counting principle is a way of counting how many different ways something can happen, and it's super simple. Here you had 2 events. I'm going to put 2 blanks. And your first event was flipping a coin. And you simply have to put how many different ways that could happen. You could get either a heads or a tails. And then your second event was rolling a dice, and you could get a 1, 2, 3, 4, 5, or 6. Multiply those 2 numbers together, there is 12 different ways that can happen. And if you count heads 1, heads 2, heads 3, heads 4, all the way through 6, then the tails 1 through 6, that's 12 ways. So how many different ways could you get heads and an even? We said. So 3 out of the 12 things that could happen would be heads and even. If you reduce 3 out of 12, I told you to put it, I'm going to put our answer down here on this number line. 3 out of 12 is the same thing as 1/4, which we know is 0.25. We know that each of these are 0.1, 0.20, 0.30, so 0.25 would be about right here, 0.25. Next problem. Now, there is another way of working this that we'll talk about later on in a higher math. I might do a supplement video if anybody wants to see how you could actually work this another way. But we're going to do it with sample spaces. So just for more room, you're flipping a coin 3 times. So your first flip, you're either going to get a heads or a tails. If you get a heads, you're either going to get a heads or a tails the second time. What if you got a tails the first time? Then you're either getting a heads or tails the second time. What if you got heads, the third time you're going to get heads or tails? These events, again, are independent of each other. Just because you got a heads the first time doesn't mean that you're more likely to get it the second time. Now let's talk about all the paths. You could get a heads, and a heads. That's one path. And you could even list these outcomes as like heads. And then you could go heads, tails. And then you could go heads, tails, heads. And you could actually list out every path. But notice how many paths there are. 1, 2, 3, 4, 5, 6, 7, 8. Was there a better way of counting that? Yes. You're doing 3 things. How many different ways can your coin land the first time? 2. How many different ways can it land the second time? 2. And again, we could have used the counting principle, multiply those together. Look, we get 8 ways. So now it says, what is the probability of getting exactly 2 heads? Let's try to identify those. You could do a heads, heads, tails. That's exactly 2. Heads, heads, tails. You could do a heads, tails, heads. Or the third final way, tails, heads, heads. There's only 3 ways. And that would be 3 ways out of the total of 8 ways. If you divide that, that's 0.375, which is about exactly 37.5%. So where is 0.37? We know this is point, and you can put 0.10 or you can put 0.100, 0.200, 0.300, 0.400. 375 would be about right there. So 0.375 on your number line is in that area. Okay, now let me show you how to do these problems with the counting principle. And this is so much easier than having to create your sample space and all this. Now, first off, keep in mind, are the events independent or dependent? So 3 standard 6-sided dice are rolled. How hard would that be? You'd have 6 different possibilities. That leads to 6 different possibilities. That would take forever to do 3 of those. But we can do this. If you just are curious about how many different ways this can happen, 6 different ways, 6 different ways, 6 different ways, we multiply it. There are 216 ways. We don't want to multiply that, or excuse me, we don't want to have to list all those different possibilities out. It'll take forever. So here's what we're doing. What is the probability of rolling 3 6s? The same way that our counting principle works, we can use this for probability as well. What is the probability that the first roll is a 6? There's 1 6, and there are 6 different ways it can land. What is the probability our second roll is a 6? There's 1 6, and there's 6 different ways it can land. The first one had no impact on the second one. These are independent. There is 1 out of 6 ways that the third one could land. So we can multiply these together the same way we multiply fractions. You get a 1 on top. You get a 216 on bottom. That's not very likely. That's saying if you did this 216 times, more than likely just 1 time out of 216 are you going to get 3 6s. Okay, let's make that make more sense. If you write that as a decimal, you get 0.004. That's not the percent. Move it over twice and you get 0.4%. Not even a 1% chance of that happening. 1 out of 100 times would be 100%, or excuse me, 1%. But 0.4%, this is 10%. If you divided that into 10 smaller places, that'd be 1%. So 0.4% would be like right there. So 0.004. Again, it means that if you write that as a fraction again, that's 4 thousandths. That means if you did it 1,000 times, if you conducted this experiment and you rolled 3 dice 1,000 times, only 4 times out of those 1,000 will this probably happen. Next one. A bag contains 5 red marbles, 3 blue marbles. Notice what I do. 2 marbles are drawn. I do 2 blanks. One after another with replacement. That's important. So we're going to draw a marble out. We're going to put it back. What is the probability that both will be blue? And a lot of times we'll write it like this. The probability of blue. So what's the probability that the first marble you draw is blue? Well, how many blues are there? There's 3. How many total marbles are there? There's 8. So there's 3 blue out of the 8. So our probability, our chances of getting a blue is 3 out of 8. It's so important that that marble goes back in, because now the probability of our second blue is also 3 out of 8. And I'll give you a second to think about, well, what if you didn't put it back in? How would that change things? So we'll talk about that in just a second. So 3 out of 8, 3 out of 8, nothing cross cancels. Multiply the top, multiply the bottom. So there's a 9 in 64 chance, which means, again, if you did it 64 times, it happened about 9 out of that 64, not even half of the time. If you change that to a decimal, you get 0.14, which is about 14% of the time. So the probability you get blue and blue, again, if you did it 100 times, that's what percent means. 100 times, it's going to occur about 14 out of the 100. This is 0.1. This is 0.2, or 0.10 and 0.20. 0.14, your percentage would be about right there. Not very likely. Again, notice how much closer to 0 than that is than 1. Let's do maybe a couple more problems. And I'm looking for, let's look for one that we don't replace, like number 6. A jar holds 10 green, 8 yellow, 2 purple. Now, first off, that's 20 total. That's going to be important. You select a jelly bean, and without replacing it, you select another. So we're picking 2. It says, what is the probability that we get a purple followed by a green? Purple, then green. Again, 2 things happening. What's the probability we get a purple? Well, there's 2 purples, and there's 20 jelly beans. Now, this is where the independence matters. Notice that you don't put it back in. Since that purple is now missing, there's no longer 20 jelly beans to pick from, okay? Now you only have 1 purple since you didn't put it back, and you only have 19 jelly beans. Now, what is the probability of drawing the green? There are 10 greens, but there are only 19 jelly beans. So that is going to change our percentage. Because there's 1 less jelly bean, that actually makes it more likely that you will pick a green one out. Then you do the exact same thing. Now, just a quick reminder from fraction multiplication, you can cross cancel here. That gives you a 1 and a 2. We're dividing both by 10. And you can actually cross cancel up and down, the top and bottom. That gives you a 1 and a 1 when you reduce that. Final answer is 1 out of 19. If you take and divide that, now here's what I like to do, 1 out of 20. Let me just show you a neat trick real quick. If you had 1 out of 20, if you multiply top and bottom by 5, that gives you 5 out of 100. Guess what? That's 5%. Since you're really close, if you multiply top and bottom here by 5, you would be really close to 100 or 5%, 5 out of 100. But you would have to multiply something by the 19 by something slightly bigger than 5 in order to give you that 100. Notice what your answer is going to be in just a second. When I divide, I get 0.053. I move my decimal over twice, and that's approximate. I'm going to put the little squigglies. That's not exact. When I move the decimal over, I get 5.3% instead of 5%, a little bit bigger. So we know this is 10%, 0, so, or 0.10, so 0.05, or you can call it 0.100 if you wanted to. So 53 would be somewhere about halfway up. So about right there at 0.053 is going to be there on your line. Let's do one more. So let's see. Let's try this last one. Maybe it's a little bit harder. A bag contains 4 red, 6 blue marbles, so 10 total. A marble is picked, replaced, a second marble is picked. What is the probability of picking a red marble first and a blue marble second? Now, this one's going to be just as easy. It's going to be, again, these 2 are independent. You didn't replace the first one. But I tell you what we'll do. What if we compare the independent version with the dependent version? The first time, let's work this problem by replace. And then the second time, we'll work it, we're not going to replace it. And we're going to see, are you more likely or less likely? So the problem says, what is the probability of picking a red and then a blue? Let me change colors here. So the probability of red, blue. There's 2 events. What's the probability of reds? Well, there's 4 reds, and there's 10 marbles. If we replace it, there's still 10 marbles. Now, what's the probability of getting a blue? Well, 6 of them's blue. If we actually multiply that out, we get 24 out of 100, which I actually like because you can type that in if you like. But I bet it's going to be 0.24, which is 24 hundredths. You can reduce that or like that, and then you can change it to a percent, which would be 24%. Now let's do the same problem and not replace it. What's the probability of red? Don't put it back, and then blue. 2 events still. What's the probability of red? Still 4 out of 10. But now let's not put that red marble back. So now you only have 3 red marbles and 9 total. So now you have 3 out of 9 would be the probability of getting a blue. Or excuse me, let's try that again. There are still 6 blues, 9 total. Now let's reduce. You can cross cancel if you want to, but I'm actually just going to reduce. 4 and 10 are both divisible by 2. That gives me a 2 and a 5. 6 and 9 are both divisible by 3, which gives me a 2 and a 3. Nothing else cross cancels. My final answer is a 4 on top, 2 times 2, and a 15 on bottom. Now I'm really curious how close that is to the 24%, which it should be fairly close. We're going to take and change that to decimal form by dividing. I actually get 0.26, and the 6's actually repeat. Move it over twice, that'd be 26.6, and again the 6's are repeating, so you can see the 2 percentages there. 0.24, let's see, this is 0.20, or 0.10, 0.20, 0.30, so 24 would be like right in there. 0.26 would be just slightly bigger, because right in the middle, think of it like this, would be 0.25. So 0.24 a little smaller, 0.26 a little bit bigger.